In this video, we're going to start to look at taking the derivative of logarithmic and exponential functions. Before we do that, let's remind ourselves of logarithmic and exponential functions and their relationship. And e to the x is the inverse function of the natural log of x, and vice versa, the natural log of x is the inverse of e to the x. And we can see that graphically if we graph them on the same plane, and we see that they are just mirror images about the line y equals x. And so they are reflected about that axis of symmetry there, and that shows that they are inverse functions of each other. A few other definitions from back in algebra is that e to the natural log of x, so if we have natural log of x in our exponent of e, that is simply x for all x greater than 0, because we can't have a negative inside of a natural log, and we can't take the natural log of a 0. And the natural log of e to the x is equal to x for all values of x. Essentially what this is saying is when you have the inverse function inside of the function, we just cancel out and the x just spits out. The one thing to keep in mind here, though, is that when you have e to the natural log of x, we are limited by the domain of the natural log of x, and so x must be greater than 0. Also here in number 2, y is equal to the natural log of x if and only if x is equal to e to the y. So we can say that if this is true, if y equals the natural log of x, well then x has to equal e to the y. And so they're interchangeable. This first one is y explicitly written in terms of x, and this function over here is x explicitly written in terms of y. Now this last rule here you may not remember from algebra, or it may have been given to you differently, or just not given to you at all depending on who your Algebra 2 teacher was. This is something important that you need to know, that if we have any real number x and b greater than 0, if we have b raised to the x, so that could be 2 to the x, 4 to the x, 18 to the x, whatever it may be, we can rewrite that as e to the natural log of b to the x, or e to the exponent of x times natural log of b. So these are equivalent, and we will need to use those to help us simplify things later on. So let's try to find out, well, if we have y equals the natural log of x, what is dy dx? That's our goal here, to find how does the natural log of x change with respect to x. And so in order to do this, we're going to rewrite this, and because we don't know what the derivative of natural log is. However, after the end of this, we will know, and it will be a rule that we can stick with. But let's rewrite this. Instead of y explicitly in terms of x, let's write x explicitly in terms of y. So rule 2 that we saw on the last slide, we can say that e to the y is equal to x. And so these two equations are equivalent, and we didn't change anything here other than we do need to keep in mind that our domain is still constrained by the first function, and that x has to be greater than 0. So if we have e to the y equals x, let's take a derivative of both sides with respect to x. So we're going to do our implicit differentiation here. And when we take the derivative of e to the y, we get e to the y, but then a dy dx pops out, just like we had in any of our other functions that we were differentiating implicitly. And when we take the derivative of x, we get 1. And so to solve for dy dx, we just have to divide by e to the y, and we get 1 over e to the y. But if we notice, what is e to the y? E to the y is equal to x. So that tells us that dy dx is 1 over x. And so we can answer our original question, when y is equal to the natural log of x, the derivative of the natural log of x with respect to x is simply 1 over x. If we look at this graphically, the graph confirms what we just showed analytically, in that if we look at the natural log of x here and this curve that we have there, well, how is that curve changing? Well, as we get close to 0, our slope is infinite, and so we need to come from infinity here when looking at our derivative. And so if we graph our derivative as we're approaching 1, we're getting close to a slope of 1, and then as we are approaching infinity off in this direction, we're approaching a slope of 0. And so when we graph that, we see that, well, that is just the graph of 1 over x when x is greater than 0. Now, what about that other piece? Well, we're limited by the domain of the natural log of x. We can't have a 0 or a negative inside there, all right? So we only have everything to the right of the y-axis. However, if we look at a slightly different function and we look at the natural log of the absolute value of x, we see that we get that same curve over on the left side, and the derivative of that curve is going to give us the other piece of the hyperbola of 1 over x. And tomorrow you're actually going to analytically derive this right here. So from that analytical derivation and the graphs, we can come up with a rule for the derivative of the natural log of x. Anytime we have just the plain derivative of natural log of x, that is 1 over x for x greater than 0, and the derivative of the natural log of the absolute value of x, that's 1 over x for all x values not equal to 0. However, what if we have a function inside of the natural log? So we have a composite function, a function inside of the natural log function. As long as this function inside that we're going to call u is differentiable at x, then, and u is not equal to 0, that is important because it's inside the natural log, then the derivative of the natural log of the absolute value of some function u is going to equal u prime over u. So the natural log, the derivative of the natural log, puts the function in the denominator, and then we, because of the chain rule, pop out the derivative of that inside function. Let's take a look at this graph here at figure 3.51, and what this is illustrating is several different functions that are in the form of y equals some number b raised to the power of x. And so we have a few different options. We have 10 to the x, we have 2 to the x, and 1/2 to the x, and the graphs are shown here. And we want to look at the slope of the tangent line at x equals 0. Well, all three of them are different. And if you notice, the slope is the natural log of b. Now, you might ask, well, how are we going to pick that out? And that's not something that you can necessarily eyeball and see that right away. But that is true. If we look at the slope here, at x equals 0 for all of them, the slope of the black curve here of y equals 2 to the x, the slope is the natural log of 2. At y equals 1/2 to the x, the slope is the negative natural log of 2. And that is, keep in mind, the natural log of 1 over 2, because really what is 1 over 2? That's 2 to the negative 1. So the natural log of 2 to the negative 1 is a negative natural log of 2. Use your log rules to get the negative natural log of 2 is the same as the natural log of 1/2. And then finally, y equals 10 to the x, our slope at x equals 0 is going to be the natural log of 10. And so this isn't a coincidence. It's the same for all functions in the form of y equals b to the x. The slope at x equals 0 is the natural log of b. So this brings us to another theorem that if we have b greater than 0 and b is not equal to 1, because if b is equal to 1, then this is a pretty boring function, then for all x values, the derivative with respect to x of b to the x is equal to b to the x natural log of b. And so keep in mind with what we did previously, we looked at, well, what was the slope at x equal to 0? So if we put a 0 in here, we get b to the 0 natural log of b. Well, what's b to the 0? That's 1, and we're left with the natural log of b. So for a mini assignment in addition to this video, I want you to come up with a rule that tells us what the derivative of the log base b of x is going to be. So once again, you're going to treat this very similarly to what we did with coming up with the rule for the natural log of x. And I want you to have y equals the log base b of x, and rewrite this function as x as an explicit function of y, and then implicitly differentiate, and find me dy dx. So do that before you come into class tomorrow.